So last meeting we talked about this related SAGE worksheet on processes, words, and how to draw Markov chain and hidden Markov chain models. So hopefully you've worked through that. I tried to make that worksheet a little more pedagogical, how to do things, and asks questions you should answer for yourself. So the previous lecture was just introducing Shannon's notion of information, which he just sort of posits is a degree of surprise. The less likely an event is, the more surprised you are when it occurs. And he says that corresponds to more information. And then he introduced this functional form. The average degree of surprise is that negative sum over the events, probability events log probability of the event, right? Where minus log of the probability is where he's sort of arguing. He calls that the self-information, and kind of starts things from there. So a lot of what we're going to be doing is, in a sense, exploring this notion of uncertainty or entropy or information, and then trying to adapt it to talk about these complex nonlinear processes that we've been studying. Hidden Markov models, nonlinear dynamical systems, chaos, and so on. So this lecture is following the Cover and Thomas book pretty closely, except, again, at about 35,000 feet. So we're covering the two most important notions in information theory, namely, what does entropy mean operationally, and how do you engineer with this? So we're sort of shifting from Shannon's notion of entropy as a measure of surprise to this very operational interpretation, which is based on these two theorems of Shannon's, which he introduced in the late 40s. So we're going to talk about how to compress a process. There might be redundancy and correlation in our process, and the ways to compress that so we have a smaller, can store it in less memory. And then Shannon's first theorem is you can't compress any better than the entropy of the source. Then the sort of more engineering view has to do with communication. That was his original motivation. And it's quite an amazing result that if you have some channel which we'll define, and it has errors in it, random probabilistic errors, there is a way to choose encodings that anticipate those errors such that a receiver can reconstruct the original message without error. So this underlies, both of these underlie so much of the modern information age. It's worth going through them. We're not going to talk so much in the immediately following lectures about communication channels, although they will come up and be an important concept in the spring quarter. We're going to talk and kind of use this compression idea a bit to develop new measures of memory, information storage. Anyway, together, how you compress and how you communicate give this very operational definition. I mean, Shannon's original argument, minus log of the probability event, that's information, well, that's just an axiom or a hypothesis. And the question is, how useful is it? Well, these two theorems say that quantity, entropy, is very useful. So here's Shannon's main setup for talking about this, a communication channel. So we have an information source. There's a way of encoding messages that are generated into these so-called code words. The code words are adapted to whatever the medium of the channel is. There might be some noise, and so we describe the corruption of an incoming code word and how it generates its output with some error, possibly. Then there's a decoder that takes the noisy code words and returns them back to the original messages. And hopefully, an incoming message stream gets decoded with zero error. So there are many examples of this. Maybe the information source are fluctuations in my neural pathways because I want to tell you something, and that gets encoded through a thought process eventually into air waves. Well, the air in this room, it's a little bit noisy. Air conditioning, echo, whatever. Perhaps not too much noise, and then somehow you decode this, and then through some mysterious process, hopefully you understand what I intended you to know. Or it could be more mundane, the way Shannon was thinking about it. He worked at Bell Telephone Labs. They wanted to build electric circuits, namely the telephone system, such that you could pick up a receiver and talk, and someone at the other end, through all the static and noise, could hear you. But it's also the case when you download files on the net, you click on something. These are all communication channels. So many, many examples of this. So this is the sort of arena of discourse for information theory, a communication channel. So we need to introduce a few ideas to start characterizing this, building up to the first and second theorems. We have some random variable distributed according to some distribution P of X, and then realizations of this will be in some alphabet. We'll call those realizations messages. These days, there's kind of universal encoding alphabet, namely binary. Almost all of our machines operate in binary. Although if you wanted to apply these ideas to, say, how the brain worked in neural spike trains, you'd have obviously different encoding alphabets, different signals coming in, not discrete random variables. Okay, so this is our encoding alphabet, and then D plus here will just mean all possible binary strings, possible codes. So we have a code word which maps from a given message, some event, to a binary string, which is an element of this binary word set. And we want to talk about sort of engineering issues like how long these code words are. So just L of X is going to be the length of the code word associated with X. And as an engineer, when you're confronted with a noisy communication channel, one of the first things you have to do is build up this code book, which is just simply a mapping from every possible message to some binary word. And you can measure, how well your chosen code book is by calculating this average length, just averaging the length according to the probability of the message occurring. And we'll sometimes call this the code rate. We have this code book, we assign a rate to it, and that's just really just the average code word length per message. Imagine this process is sort of running along in time. So we have sort of an encoding. The original information source series of messages ends up coming out of the encoder as this concatenation of code words. And we can say that there's been some compression if we're careful enough in choosing the binary code words for the messages. We will have compressed the information source series of messages if this code rate is less than the log of the size of the message alphabet. So let me give you an example. That's a whole slew of definitions. An example will help make this clear. So let's imagine that the message alphabet is just little a, b, c, d, given by some distribution. So here we'll choose probably of a to be a half, b a quarter, and c and d occurring will be probably 1/8. So we have a distribution over events, and we can just plug it into the Shannon entropy formula, p log p. So there's a number. We're using log base 2, so the output is in bits. So we have 1 3/4 bits. Right, so that's Shannon. If we just plug this in, this is how surprised we are. We're doing a series of experiments, D, C, C, A. The least probable events are more surprising, minus log of the individual events probability is the self-information. Then when we average that over the distribution of events, we end up with this average surprise. We have 4 events, but we're getting 1 3/4 bits of surprise or information every time we make a measurement. Okay, so now let's be the communication engineer. I'm going to basically arbitrarily choose a set of binary code words. I'm designing the encoder part of this communication channel, and I associate with A the code word 0, so just a word of length 1, B 10, C 110, and D 111. Okay, so first observation is if now I just chose that set of code words. Like they could have been length 100 sequence binary words if I wanted, but I chose these. And I can plug that into that code rate formula. What's the average length weighted by the probability of these events occurring? And lo and behold, notice that the code rate is 1 3/4 bits also. But there's some relationship here between the entropy, this degree of surprise, and how efficient our encoding is. And the other immediate conclusion is that since this code rate is less than the log of the message alphabet size, which is log base 204, or 2 bits, we're compressing, on average, 1/4 of a bit. We're kind of squeezing out some of the, if we had just streams of A, B, C, D, and looking at how much memory we'd have to store, then if we use this binary code, we'll use 1/4 of a bit less with those code words, with that code book. So this is a huge area of research, encoding. In fact, we wouldn't have online internet video if it weren't for compression schemes and people trying to estimate what's the entropy of a movie, and then how well can I compress things. And there's obviously a lot of redundancy in movies, right? If your camera pans up to a blue sky, you don't have to transmit thousands of pixels that are all blue. What you say is, oh, here's a blue pixel, and there are 1,000 of them in a row. That's a more compressed description. So that's exactly this scheme here. And this example is just very, very simple. So I'm going to carry this example through, actually, this lecture and even, I think, the next lecture. Just simple. 4 alphabet, information source, and this particular choice of code words. Okay, but there's a problem. So I encode these words, and let's, at least for now, forget that there's any noise in the channel. I'm just going to present the code words to the receiver downstream. And the question is, the receiver is just getting this series of zeros and ones. How do those correspond to the original messages A, B, C, D? Could be ambiguous, right? So there's a series of constraints on how I can choose these code words associating message to binary code word so that the downstream observer can decode it. So the first thing you want in a useful code is that if the messages are different, you want the code words to be different. I mean, if the messages were different and you had the same code word, there would be no way that the receiver could figure out what you meant, right? Okay, so we want a non-singular code. We also think about extensions of codes because we'll be looking at a whole time series of measurements, and then we extend this to just, so C of this length L message word is just means the concatenation of the code words for that, okay? And that's what this receiver is getting. So we're actually, when we're talking about how easy it is for the receiver to reconstruct, we're talking about a stream of bits like this. So the first useful restriction is what's called a uniquely decodable code, namely that when extended, this extended code book is also non-singular for all the messages of length L. In other words, distinct incoming words of length L lead to different concatenations, so that information is preserved. The distinction between the incoming message stream and the code words is maintained, okay? So within the class of uniquely decodable codes, there's a particularly easy one to illustrate the idea. It's called a prefix code. And the idea is that no code word is a prefix of another if we're looking at different messages, which is going to help the receiver scan to pull out the original message. So this is useful because we don't have to, for example, read 1,000 bits to realize what the initial code word was. And a prefix code is uniquely decodable. So here's the example again. So remember the code book mapped A to single 0, B to 1 0, and so on. Now imagine that the information source generates this length 6 message sequence. And then how do I encode it? Well, that's pretty straightforward. I just look up for each letter what the corresponding code is. Okay, C maps to 110, D maps to 111, and so on. So you just concatenate these together. So that's fine. But now the question is, if I just gave you this binary string, how would the observer start to figure out what was A, B, C, or D? What's the framing of this encoding? And is that reconstructible just from knowledge of the codebook and the data? So we're going to run this backwards. So this decodability issue we're talking about is really talking in a sense about the invertibility of the codebook. So again, so now we're just given this 0. So we go look up here. Well, there's only one word that starts with a 0, and that's A. So I put A out here. Next one is a 1. Well, there are 3 words that start with a 1, so I've got to look a little further ahead. Now I have 2 1s. Now there are 2 messages that start with 1, and then I see a 0, so now I know it's C. Okay, so now I just reconstructed the framing, and I can translate 110 into C. And then after that, I see 3 1s. Again, sort of parsing down here, I see that's D, and so on. So then you end up realizing that this codebook is uniquely decodable. And the way we were doing that was facilitated by the fact that no code word is a prefix of another code word. They don't precede each other. And that suggests a very simple graphical way of drawing a prefix code as a binary tree. So what we do is we put a tree with branching on 0 and 1. The leaves of the tree are going to be our code words, and the paths will be the symbol sequence leading to that code word. So we think of these as the leaves are associated with the events from the information source, and the path to get there is the code word.
So then when you said about P of A, B, C, and D, where you sort of had this in mind already.
Yes, that example was completely concocted to show you the best possible case. Right. So we'll work with that first.
It being 1.75 bits, is that something that's just stated or something that we can see from here?
Oh, well, no, you directly calculate, right? You know that A occurs with probability half, and that's length 1. B is probability a quarter, that's length 2, and then C and D are both length 3 and occur with probably 1/8. So that that's just a direct calculation in that rate code expression. Right, and I was just kind of curious. Oh, this rate code thing, which is like a performance measure, is equal to this funny P log P expression of the distribution. So what's going on here? So that's what we'll talk about. We'll kind of unpack that a little bit. Okay, so one of the things you notice in this, I mean, this is, you might think of the tree that I've laid out here. It's a little bit sort of like what the encoder is doing. It's like, oh, a B just came in from the information source, and I should output 10. Oh, I just got a D. I should output 111, and so on. It's kind of a mechanistic description of the encoder. There's another thing to notice is that if I look at, kind of weight the transitions going down here in terms of 2 to the minus the length, we end up with these weights all summing to 1. And that's something that's going to come back. But that's the nature of being a prefix code. And that's summarized by what's called the Kraft Inequality. I won't go through the proofs of this, but you can show that prefix code books, because they have this binary tree structure, satisfy this sum over 2 to the minus length of each message, that being less than or equal to 1. The example I just showed you, it saturated, that was equal to 1. So, and that is, you might think of this as an algebraic way of expressing the prefix property. That'll be useful for an optimization problem. Yeah.
So are there cases where this is less than 1?
Yes.
Okay.
Yeah.
And all this is in binary.
Yes, we're just doing binary. I think Cover and Thomas do the general case, but binary. All our machines are binary, so it's in some sense general. Okay, so why do we need this? Well, one question is, especially to get back to this issue of how did that code rate calculation, average length over event of messages, relate to the Shannon P log P formula, the average uncertainty. So what we're going to do is we have to answer the question: how are these code word lengths related to message probabilities? I mean, I chose them in a certain way. I mean, maybe I should just state the sort of the obvious, that if you want to compress something, what you do is you take a high probability event and you give it a short code word, and then low probability events, you give them longer code words. So if this is going to occur a lot, then I'm using fewer bits to represent it. If it doesn't occur very often, I can afford to have longer code words. And doing this cleverly, like this sort of optimal case here, you can get this ideal compression that's adapted to the events and their probabilities. In some sense, it's almost like the code words are encoding the probability, code word lengths are encoding the probability of the events. So that's what this Kraft inequality does. So what we're going to do here is there's an engineering problem. How do we, given messages and their probabilities, how do we choose code word lengths? So we want to find some codebook, or the constraints on what these code word lengths could be. So what we're trying to do in optimizing this is minimizing this code rate, the expected length, subject to this decodability for having a prefix code. There are other kinds of codes, but this is just the simplest one to get the idea across. So we have these two specifications, and the typical way you satisfy these is to use Lagrange multipliers. So we have, in a sense, sort of a total cost here plus this length constraint, and we put in this Lagrange multiplier. And then what we do is we look at, for each message, where this is 0, the optimum for that. So just take the derivative through here, and we end up with the probability minus lambda 2 to the minus length of the code word. And we have to be careful about the logs here when we're taking the derivatives. Log base e of 2 pops out. Or the other way to say this is that 2 to the minus code word length is the probability over this normalization factor. So we have this constraint, when this is equal to 0, that this lambda, Lagrange multiplier, is just 1 over log base e of 2. And the conclusion is that the optimal codebook will have lengths that are log of the probabilities, minus log of the probabilities. So this was Shannon's argument for the self-information of surprise, but now we've just derived this way to engineer, or at least a criteria, there's still some subtleties here, for what the code word lengths should be. We're not saying what they are, it's just a constraint on their lengths. Yeah?
So in a real code, our lengths are all integers, so we need to kind of...
Exactly, yes.
Constrain.
And then things get interesting. Yes, right, so I'll get to that, right. Right, so, and then of course if I average this over the event probabilities and average this over the event probabilities, lo and behold, we in a sense have derived this optimization that this degree of surprise, Shannon surprise, the unpredictability is actually the average code length for an optimal code. So, however, this is not an integer. So those numbers we just calculated, the relationship is actually just the ideal case. I mean, I either have a bit or I don't when I build my hardware. When you go down and buy your memory stick, they don't give you half bits. You buy whole bits. So there's a problem. And this leads to a huge range of alternatives for encoding. And the book goes through maybe 3 or 4 different coding types, Shannon, Fano, and Huffman coding. We don't have time to do that. I just want to get the idea of compression across. Right, so a simple thing you could do is you look at your messages, their probabilities, look at this surprise, and then just take the integer larger, next integer larger as your code word. But that can be inefficient. So there are various classes of coding schemes that were developed early on, and typically you can kind of bound them so that the constructive coding schemes, their lengths are between the entropy rate and the entry rate plus 1 bit. But even that can be a large cost if you're looking at messages of length thousands. If I'm adding a whole new bit on every time, that can be bad. So these codes are not optimal. And there is a subfield called coding theory that tries to make this all work. Like I said, all of the sort of online audio and video is driven by encoding. A movie, feature-length movie, you couldn't broadcast or even transfer it over the internet at full 35mm resolution unless you had compression. So it's all using this idea with very, very fancy, what they call codecs, coder-decoders schemes. Taking various things into account, like, oh, there's blue sky, or skin has a certain range of colors, or and so on. You can use that with extra knowledge about the structure and objects in the source. You can use that to compress these things. So these are just simple examples of those kinds of codes. Okay, so to sort of kind of set up for the first Shannon's first theorem, we just imagine that we have some information source distributed according to P of x, but somehow when you're engineering it, you have misguessed the actual true distribution. The question is, how bad is it? So you can show that if you have the incorrect probability model, then what you end up with is and then you design to that, then this average code length is going to be the sort of the true lengths you should be using as reflected in the entropy, Shannon entropy, plus the information gain, or the Kullback-Leibler so-called distance between P and Q. It's the number of bits that the two distributions differ. And this will be the typical situation, because ahead of time you're not going to know what the probability distribution is. You might be transferring a movie, or you might be transferring a dictionary over the same channel, and you can't usually design an encoder that knows all of those distributions or even identifies them to know which distribution you should use. So typically, encoders just makes various kinds of guess. They try to be a little bit adaptive, but you'll never get the distribution right. And as a consequence, you're kind of stuck with this error term here. And this is the best you can do. You can also come up with a terrible scheme and have a codebook length that are much larger. So Shannon's first theorem, the data compression theorem, basically summarizes this. Namely that given some information source, calculate its entropy, you just can't do any better, however you encode it, than that. This is fundamental limit. So the other way to say this is that you can't compress an information source below its source entropy rate. It's this fundamental limit. And therefore, it's, when you can estimate the entropy of a source, it gives you the first sort of constraint on how you're going to engineer your encoder, what sort of rates of performance of the system you're going to have. And it gives us this sort of operational meaning, as opposed to just, oh, I'm surprised, oh, that was an unlikely event. It actually has consequences for when you're designing an encoder and trying to compress. Sometimes it's useful to have a kind of performance measure. So we talk about the redundancy of a random variable. Kind of imagine we have two things we can do. One is I have my message source and I just transmit those messages, A, B, C, D, whatever, and pay all the hardware costs for doing that and transmission time and so on, versus knowing what the actual distribution is. So we look at the difference between the sort of identity code book, which is this log of the message alphabet size, and the entropy rate, which is this lower bound. It's the best you can do in terms of compression. And to the extent that there's a difference between these things, you'll get some compression. So we call that the redundancy. In the original message source, to the extent the redundancy is positive, there are correlations you can take advantage of to compress. So in that example, we had ABCD, four-letter alphabet, so that was basically two bits. If we just transmitted ABCD as it came up, versus the entropy of that source, because the events had the skewed distribution, we ended up with a entropy rate of 1 3/4 bits, so there's about a quarter bit of redundancy somewhere in this source. You just know, without actually having built a code book yet, you just compare the Shannon entropy to log of the alphabets, or message size, message alphabet size, to see if there's something worth trying to compress. So now what's interesting about this is that, like in that example, typical messages, whether I'm speaking or reading a dictionary or reading Goethe's Faust, they're redundant. There's correlations. That's important for meaning, readability, and so on. But once we've done this encoding, the output stream, the encoded stream, if we've done it well, actually is not redundant at all. We have a new stream that actually, if we did it right, would be the entropy rate. So what that means is when we encode things, when we kind of squeeze out the correlations and regularity, what we end up with is a random source that looks just like a fair coin, if we've done our encoding well. In other words, we saturate that limit from Shannon's first theorem, that the code rate will be this. And then we end up with just random bits coming out. So of course it might seem a little strange. Wait, it's random bits. How does the decoder ever decode these? Well, that's where that framing comes in, and knowing what the structure of the code book is critical. Because every bit in the encoded compressed stream is maximally informative. You have to know exactly where to pull things out, how to frame it to interpret and extract the original message. Okay, so that's kind of Shannon's idea of compression. Again, it's this operational meaning for his measure of surprise. You just can't compress any more than that. So now, sort of more powerful and interesting result of Shannon's information theory is the way he uses this to talk about communication channels and put bounds on reliable communication. So it might seem a little bit strange in this communication channel that if the channel corrupts the messages coming through or the code words coming through, how can it be that a receiver could ever reconstruct an error-free message and do that with positive probability? So now it might be the case, like Shannon was working with, at the Bell Telephone, that they had some knowledge of the kinds of errors that would occur. So is there some way, there's now an additional constraint. Instead of just maximally compressing the signal, squeezing all the regularity out, in a sense you want to add regularity back in that anticipates where the errors are going to occur. So, and the amazing thing is there's basically a positive answer to these questions. So this notion of channel, it just applies everywhere, like I mentioned. Talking on the phone, even your HTTP transfers, a dynamical system at some time t and its next state. You can think of the dynamical system as communicating its past to its future as a communication channel. It's a communication channel over time. You can have a spatially extended system, like the logistic lattice. You can talk about how one spin in the system is communicating to another one and ask how correlated they are. Think of that as a communication channel. We'll talk about examples like this. Measuring instrument, Markov partitions, generating partitions. Those are all channels, right? We had an orbit over a dynamical system, continuous state space, and we ended up with the symbol sequence. That's an encoding, and we can ask all these questions. How good of an encoding was that? Well, we were implicitly already talking about these ideas when we said that a generating partition is good if you look at sufficiently long binary sequences. That's an encoding scheme, building a code book. And also, in a sense, even that overall learning channel. You can think of that also as a communication channel. We have sort of complicated nonlinear nature somehow observed indirectly through this measuring instrument, and we want to build a model of it. So we're trying to figure out what the internal states are. So the very act of building scientific models from data can be thought of as a communication channel. You're trying to find out what messages Mother Nature is trying to express to us, except we always have this indirect view of what's going on through a measuring instrument. And it goes on and on. The concept is very, very broad, and we'll use it in a couple different ways later on. But first we have to understand what Shannon taught us about error-free encoding. So the problem of transmitting messages error-free over a noisy channel breaks down into two kinds of things you have to anticipate. So the first one is called equivocation, namely that the same input leads to distinct outputs. Right? I say some word, but then there are two different possible things you could have heard. So that's one kind of error that a noisy channel can introduce. It misrepresents the input. The other, ambiguity, in fact this is almost the more difficult one, two different inputs lead to the same output, so that the receiver seeing the output of the channel can't tell which input is coming in. Here, okay, it's noisy, but I could still figure out what the incoming message was. So I can kind of correct for that. This is bad. That's particularly bad. In some sense, the output doesn't have the information you need to figure out which the inputs. So the strategy in kind of behind Shannon's construction of the second theorem is we want to find channel inputs that are least ambiguous, that are distinct, keep them far apart from each other, so we don't have, if we have a whole series of these things, that the outputs won't overlap. And then build our code book so that we map the original messages onto those inputs to the channel. Right? We're sort of matching up the information source with the messages coming in. And we know how to compress that, so we're just going to imagine we have an ideal random sequence coming into the channel. And then we have the channel characteristics we're trying to match back to that. Okay, so here's the setup for the second theorem. So we're going to imagine that we have a channel. There's an input. It has some distribution, P of x. Channel output, it has some marginal distribution, P of y. And we're going to describe the channel with this conditional distribution. Right? Given an input, what's the distribution of outputs? So I'm now just formalizing that picture of equivocation and ambiguity. That's all in some matrix, some conditional distribution here. And typically, the way you see developments of this, and this is certainly true of the Cover and Thomas discussion of all this, it's possible that the output of the channel could depend on the previous history of the inputs, but typically not. We're just going to assume a memoryless channel. Current input leads to some set of outputs, no history. And everything I'm going to say is going to assume a memoryless channel. Now we need some performance measure, and that's this channel capacity. What we're going to do is look at the shared information between the inputs and the outputs using the mutual information, and then maximize that over all possible inputs. This will be some way sort of a best case scenario for a channel. So we have a channel, we're going to characterize it with this mutual information when we look at all possible inputs. So basically the idea here is this channel capacity is the highest information transmission rate from inputs to outputs that you could expect. Could be worse. So this mutual information is sort of an interesting quantity here when we're thinking about inputs versus outputs. They're really sort of two extremes, and we'll run across this in other settings of sort of no communication. So I have an input and output to a channel. They're two sort of extreme regimes where we have no information flowing through the channel. One is we're not sending any information in. The input source is completely predictable. There's no information in it, no entropy. And then in this case, of course, we just write out using information identities, the definition of the mutual information, uncertainty in the input minus the uncertainty in the input given the output. Both of these are 0 because there's no information coming in. And there's sort of this interesting complementary extreme of complete distortion where the input and the output are statistically independent of each other. And that also leads to, if you remember, that's just a basic property of mutual information. If the input and output are independent, there's no shared information, there's no mutual information. Yeah?
So what does it mean when you write max over P of x of I of x?
Over here? Okay, so this is the mutual information between input and output, right?
I thought that was just a number.
And then what I'm doing is, right, so x here is distributed according to this distribution. So I just imagine I'm looking over all possible inputs.
Okay.
An example would be, imagine that x was a bias coin, then its distributions would simply be parameterized by the bias. So this would just be looking over all possible biases, and which bias coin has the most entropy? Well, that would be the fair coin.
Okay.
Okay, so that's the idea. I mean, this is a little more general than that, over all possible inputs. I could have, the Gutenberg Bible, or, a river runs through it movie, whatever. That's any possible source.
Okay.
Yeah. Again, so we're just trying to look at how much could we get through the channel. It's this channel capacity is this performance measure, and this is the best you can do. in terms of maximum throughput over all sources. So we're working with this duality, namely on the encoding side of the channel, we're trying to compress because we want to remove the redundancy, basically push as little information into the channel as possible. And then once we have this compressed description, then we can strategically add redundancy to compensate for the channel errors. Maybe they're, frequency limitations or amplitude limitations of some analog channel, for example. You exceed those, then there would be errors. In hard disk drives, it turns out that as you write your bits on the magnetic platter, that if you write a long series of ones, the detection electronics starts to drift, and the error in reconstructing the signal gets bad. The longer the set of ones or longer the set of zeros. So you have to make an encoder, even when you're putting your PhD dissertation down there, it's broken into runs of finite length. So there aren't too many ones or zeros. So there's a limit like that. So anyway, magnetic channel has its own kind of physical characteristics that you have to compensate for. Okay, so just some examples of channels. And these are actually kind of the base cases we need to understand the essence of the coding theorem. The first is just a noisy binary channel. So here's the channel, dashed line, 0 comes in, A comes out, 1 comes in, B comes out. Okay, seems kind of trivial. Input alphabet, output alphabet. The channel is described by the identity matrix. Nothing subtle going on here, but let's go through the calculation. What's the channel capacity here? Again, we're maximizing over input distributions and mutual information. I can just rewrite. In fact, the trick in these calculations is figuring out which form of the mutual information you want to use. So I just rewrite entropy of the input minus uncertainty input given the output. Well, since this is the identity channel, there is no uncertainty in the input given the output. We know that. Okay, so that's 0. And now we're just maximizing the entropy of the input. Well, that's going to be just a fair coin. Okay, so obviously, good. That case is simple. Next one is the noisy channel with non-overlapping outputs. So binary inputs, 4-letter alphabet in the output. And here's the channel. 0 comes in, and with equal probability, the channel distorts the 0 and puts out A or B with equal likelihood. Same thing with the 1, with probably 1/3, 2/3, say. It outputs C and D. But you can kind of tell. If I tell you A, you know what the input is. If I tell you D, you know what the input is. So this is not so bad. It's distorting things, so that's not good. Maybe it's fuzzing up your image, but you can still see there's an ice cream in front of you, right? So it's okay. Again, the calculation is relatively straightforward because of the property I just mentioned. This uncertainty in the input given the output is 0. I can reconstruct from the output what the input was. And then again, this calculation just reduces down to maximizing the source entropy. That's just 1 bit, and again, for a fair coin. Now maybe a sort of more realistic example is called the binary symmetric channel. And it's going to have an error probability. So this is real errors here coming in. So if a 0 comes in with probably 1 minus E, it'll be faithfully transmitted. But with error rate E, it's going to be flipped to a 1. And same thing with a 1 coming in with error rate E, it's going to be flipped to a 0. Okay, so now this looks particularly troubling. You look at this and you think, well, how, if I look at this output stream of 0s and 1s, how can I ever figure out what the input was? Well, Shannon showed that even in this case, you can find good codes. So the output can be matched to the input exactly. Okay, so how do we do this calculation? Again, we're just focusing on the mutual information. In this case, it's a little bit easier to write it down using information identity is the uncertainty output minus the uncertainty output given the input. Well, what's the uncertainty in the output given the input? Well, that's just for think about each case here. There's just this little very biased coin that's choosing error or not error. So that's contributing an H of E. So think of this as little biased coins being flipped inside the channel that's causing the error, and that gives that uncertainty. So the uncertainty in the output given the input is just E or minus E. Okay. And then, as usual, I'm maximizing over the inputs again, but you can see just because it's symmetric, if I put in a fair coin here, I'm going to get a fair coin on the output just because of the symmetry of that. So that means that this uncertainty in the output is just a fair coin, 1 bit. So, so we end up with this being the channel capacity, 1 minus h of the error process. Kind of makes some intuitive sense. And then notice that when the error is 50-50, in other words, a 0 comes in, but a 0, 1 comes out with equal likelihood, you can't transmit anything, is what it's saying. When e is equal to a half, this goes to 0 because h of a half is 1. So that there can't even leverage anything. There's nothing to leverage when the error rate is 50-50.
So just to be really clear, h of e is just minus log of e log base 2 of e?
Let's see. Minus e log e
Yeah.
minus 1 minus e log 1 minus e.
Oh, okay. There we go.
Right. So we're summing over the two events. Yeah, think of this like inside there's this little thing. Should I make error? Not making error. And I have two events. What's the entropy of that little random event source, h of e? And it's reducing what I could, right? If e is equal to 0, then we're back to the ideal identity channel as before. And then we're just kind of peeling off a little bit, and it's throwing some information away. How much? That much. But what's interesting, as we'll see, is that even in this case, this is a channel you can actually do error-free information transmission on.
And so the achieved when source is q of x is 1/2, 1/2.
Yeah.
What's that stating?
Oh, okay. So that's just, remember, we want to find out this I is sort of this information transmission rate through the channel, but that depends on what information I'm driving the channel with. So the capacity is just trying to remove that dependence and find this kind of best case. What's the best information transmission rate over all inputs? So that's how the capacity is kind of crafted to measure that kind of best case transmission rate. Okay, so talk a little more about channel capacity. You can show, since it's a mutual information, if you remember back previous lecture, mutual information is non-negative. It's actually bounded above by both the log of the input alphabet size and the output alphabet size. A very important property is, since we're doing this maximizations, you can show it's continuous in the input probability distribution. In other words, if I had like the bias coin with a parameter bias, this number varies smoothly as I vary the bias in the input signal. So that's nice. It's also a concave function of this, and that's actually really important because with these two properties, you can show that there's always a global maximum. I have an optimization problem here. I'm saying maximize this over the space of input sources. This thing is this nice, well-behaved function that I can do hill climbing optimization on because of these two properties. So suffice it to say that they're nice optimization algorithms for this. You typically can't solve, if I throw down some random channel, memoryless channel, you don't, unlike we just did, you can't write out the capacity in closed form, but you can approximate it numerically because of these nice properties. So that's where a lot of communication engineering is done, is actually doing a numerical optimization, searching around in the space of, of input distributions and calculating this, trying to find the maximum once you design your channel. Good to know how well it can perform, yeah.
Wait, so we were optimizing over space of distribution?
The input, yeah.
The metric there is the Kohlbecker, the probability metric. And what is it like? The metric on the space of probability distribution, right? The KL.
Oh, yeah. It's not really a metric, right? But we use that as it's used very widely to measure in informational units how different two distributions, say P and Q are.
Yeah.
That was that D, P, double bar Q. That's a funny notation. And it's really, you'll hear people say, call it the Kullback-Leibler distance. It's not actually a distance or a metric, but it has properties that are very close to that and good enough for the uses we have for it. So when the two distributions P and Q are the same, it's 0. It comes in units of bits, and you can think of if the distance, this DKL is information gain, sometimes called, is 3.5 bits. It means there's sort of like 3.5 bits of difference in the distribution. You kind of map one into the other if you flip 3.5 bits. Yeah, but it's not an actual distance that's symmetric and triangle and like that. But there are other things. In fact, I think we mentioned it in last lecture, just the basic information theory. There is a bona fide distance between distributions, and it's the sum of their conditional entropies. So h of x given y plus h of y given x. That is, you can actually show that that satisfies a triangle inequality when x and y are zero, are the same, it goes to zero, and so that's a true distance. The problem with that is they're conditional entropies, which means I have to know the joint distribution between the two variables. The information gain in a Kullback-Leibler number is actually, I just need the marginals of the distributions. So the trade-offs, and it gets used very, very widely. Okay, so this is the pièce de résistance of early information theory, Shannon's channel coding theorem. So this capacity we've been talking about is the maximum reliable transmission rate. In particular, very constructively, or I shouldn't say it, very helpfully, it says that if the information source and then the way you're encoding it, its code rate is less than the channel capacity, then there exists some encoding and decoding scheme such that the receiver can extract the original messages with zero error. So for that binary symmetric noisy channel, that's, it's kind of surprising how you can actually do that. I'll give a very quick sketch of what the argument is. It's basically that we want to think of this noisy channel in terms of that non-overlapping output case. Remember this example here? This guy. Noisy channel with non-overlapping outputs. What we're going to try to do is encode things, actually over long messages, such that even if there's error, the error that's being introduced by the channel only does this kind of thing, so that we can still get sort of maximum transmission rate. Right, so what we're going to do here is look at not individual messages, but actually sequences of messages. And so we sort of know that, roughly speaking, if if the length L messages were all equally likely, there would be 2 to the L of them. Well, there's some, imagine in the general case, they will occur with different probabilities, and so we're going to weight that with the entropy rate. So the number of distinct incoming messages basically scales as 2 to the length of the message sequence times the entropy rate. Remember, we're using this because we just compressed everything as much as we could. That's really all that are distinct in the length of messages. And then what we want to do is then the next engineering step is to choose code words, the inputs to the channel, such that when they go through the channel, they produce non-overlapping outputs. Even if they get corrupted, the output is still non-overlapping, so we can reconstruct. So here's the kind of a cartoon picture of what's going on. We have our inputs, there's the channel, and then outputs. We're just kind of arguing that the input space is this circle here, and the size of that is something like 2 to the L times the entropy of the source. That's the number of distinct messages, kind of the volume of those. Then somehow this noisy channel acts and takes these things and fuzzes them out, just like in the non-overlapping case. And if we want them to not overlap, we have a packing problem. So here's the output space, right? There's some entropy of the output, and then its volume is going to be sort of governed by 2 to the L times the h of y. And what we want to do is, in this output space, pack as many of these noise ellipsoids as we can. So the question is, how many of these individual incoming code words that map to these fuzzballs, how many can we pack in here such that they don't overlap? Well, we know roughly we know how to monitor the size of this, the noise in the non-overlapping outputs, right? That's basically governed by the uncertainty in the output given the input. So we've given an input, how much does it spread out? Well, the volume of that is basically given by this conditional entropy. And I'm now doing 2 to the L just to kind of count distinct number of words. So we're kind of comparing the output space to these little fuzzballs, and the question is how many of these can we fit in there? And there's just a very simple calculation that shows what the role of mutual information is. So the total number of disjoint output sets that we can pack in here, that's just simply this ratio. That's the large volume, the large oval there, divided by the typical size of these air ellipsoids. And then notice what we do here. That ratio, this number of ellipsoids that we can pack into the output, it turns into this 2 to the L times the difference between the output entropy minus the uncertainty in the output given the input. And that's just 2 to the mutual information. So that's why this mutual information pops up and is such a key quantity. It's actually measuring how well you can pack these non-overlapping outputs into the output space. So, in other words, just to kind of re-say it, you can send at most that many messages of length L. That'll still be distinguishable and therefore reconstructible. So, the conclusion is that this channel capacity is the maximum transmission rate. And it really just turns into a lot of coding theory. The practice of it is really studying packing in high-dimensional spheres. So we're looking in spaces of dimension L, signal spaces of dimension L, and then looking at how many of these air balls we can pack in. So that's sort of surprising. The Shannon's proof is non-constructive. It just says it can happen. It's not telling you what the code book should be that will do this. And that's why there's this huge industry in coding theory of trying to come up with all these different kinds of encoding, decoding schemes. So that's also, remember the condition was that for error-free transmission that the code rate was less than the channel capacity. But what happens when, say, in like a real experiment, we don't have that. So there's this kind of overall picture. Imagine that we had this horizontal axis here, different code rates for different sources and different encoding schemes. And then we have a channel that we're trying to get the information through. And so the good part that the second coding theorem deals with is when R is less than C and we can transmit error-free. But then as soon as the code rate gets above the channel capacity, then there's some probability of error, of unreconstructible error, irreducible error in the output. And this is actually, I would say, kind of the typical situation when we're doing experimental work. We don't really know. We're designing the instrument, this measurement channel. There's lots and lots of information in the system we're studying. Turbulent fluid, we put in 3 probes. Well, okay, there's lots of things those 3 probes aren't picking up. Nonetheless, we still, can extract some features and still do some science. So this is kind of the ideal engineering regime where the code rate is less than the channel capacity, and sort of above that is, I would say, kind of the typical case. Of course, we try to do better and better as we design our instruments and choose what probes we're going to use. But probably it's fair to say that a lot of the experimental work in the sciences is way above that. So we don't really have that solid a characterization as below, as in the error-free regime. Okay, so that was a whirlwind tour of information theory. Yeah, I mean, I'm sorry that it's so brief. I would urge you, if you find it interesting, to read more in Cover and Thomas. There's certainly courses on campus that go through this in quite some detail, and seriously, not at this kind of synoptic level we did. The reason is we have other fish to fry. So what we're going to start doing is take these basic notions of Shannon's measure of information or entropy, notions of compressibility, and to a certain extent, channel capacity, and adapt them to start to describe and come up with measures of how dynamical systems generate information, store information, throw information away, and so on. So that's going to be the subject for the next couple weeks, is how we take these basic ideas. I mean, I pointed out that the channel coding theorem is just for memoryless channels, but in fact, we're dealing with memoryful processes. Right? The Rössler attractor has a shape to it. It's not just hopping randomly in its state space. It actually has some geometric shape to it. How do we capture that? And can we measure that informationally? So we'll start talking about ways of taking Shannon's notion of information, which is a notion of surprise. It has a very natural interpretation when you look at dynamical systems as a measure of unpredictability. And we'll relate that back to these Lyapunov exponents, which is a more geometric picture of instability in the state space. But then the next step is, well, systems typically also remember part of their past. How can we measure that? So we'll extend, just like in the coding theorem, we're going to take Shannon's entropy and apply it not to single events, but to sequences of events, sequences of measurements. And you'll see there's some very natural quantities of memory that fall out from that.